Okay, so welcome to this session. Thank you for being here. Until now, you've seen during the sessions how to access the clusters, how to copy data to the clusters and copy from the clusters, how to choose and activate software with the module command that lists the available software and so on. You've learned how to run software in the command line with a game shell. You've learned about Vim for creating and editing files. But you still actually need to learn how to run the software on a cluster. And this will be the topic of this morning's session. The short answer is that you don't run software on the login node. You submit a job to a piece of software called the resource manager or a job scheduler. So here I've been talking about two things, jobs and resource manager job scheduler. So what is a job in the context of computing? It's an operation or group of operations treated as a single unit. So actually you get to decide what a job is. It will most of the time be some program that generates data or some program that consumes data and produce results. But you decide what you get in what you put in your job. The second important term was the scheduler and resource manager. So this is a piece of software that does two things. It first organizes the resources in the cluster and decides when a job can access what resource. So the resources in a computer have been described earlier by Frédéric, but this is a typical compute node with the main component being called the motherboard. It's a main circuitry inside the computer on which all the resources are plugged. And what provides the compute power is mainly the CPU. This is a CPU socket which is plugged in here. And inside here we have multiple CPU cores, and each core is capable of computing. It uses memory, so random access memory, which is plugged here with the memory during the time of the job, volatile memory. It has disks with long-term storage. Actually, in compute node, you will see that the storage is limited to the period of your time, to the duration of your time, and GPUs, which are a specific type of compute engines with specific capabilities, for which we have like 3 training sessions in the future. Very powerful, but a bit difficult to use. So this is the director. So back to scheduling. The idea of scheduling is what? If you think of the cluster as a set of resources over time, you can see a job is consuming some amount of resources for an amount of time. So we can draw this as a rectangle in here, and this would be what we call the completed job. It has used for this duration all these resources, and it's done. This job is running. This one is 2, and these 2 are pending jobs. So jobs that are waiting for the resources to get freed so that they can start. And then, given this situation, at some point, users will submit additional jobs, which I presented there. And the goal of the job scheduler is to organize the jobs in the future and decide that this job and this job will start both at the same time here. And when this one is finished, this one can use a whole cluster for a short duration. So the main idea is always to have an exclusive allocation of resources to job. So if for your job you request, let's say 12 CPUs and 2 GB of memory, you are sure that when your job starts, you have those 12 CPUs and 2 GB of memory. And no other job can use those resources. They are exclusively allocated to you. So this always reminds me of a game I played when I was a child, but as time goes by, I realized that most of you never played this when you were younger. But anyway, here is not Tetris, but the name of the scheduler is called Slurm. So Slurm is a piece of software that's used by over 65% of the largest computers in the world. So it's basically universally seen as the standard in high performance computing on clusters. It's open source, it's free, and it's been created in around 2003, so it's rather an old piece of software, very mature. There's a very active community, many success stories, and also it's the name of an intergalactic soft drink. And this is a proof of this term. Of course, the author said that there is no link. We know. So what we'll be talking about today, we'll see first how to create a job. And you will see it very easy. You write a text file and you run a command, and all this you can already do. We'll discuss a very important but difficult point, which is how to choose the resources. Okay. I'll talk a bit about the priorities, because most of the time we have more jobs than we can afford on the clusters. So there is a ranking, and people's jobs go before some other people's jobs. And it's all orchestrated by priorities, and it's important that you understand the priorities because they are made to make sure that everyone has a fair access to the cluster. And I need you to be convinced of it, so that's why we explain how it works. I will give examples of typical workloads because everyone's workload is a bit different than other people. You will see that there are workloads which need a large number of CPU at the same time, others which need more memory and fewer CPUs and so on. And then I'll talk about interactive sessions. And this is important because, as I mentioned earlier, you're not supposed to work on the front end, but some workloads are not easy to run on batch scripts. So Slurm offers options to run interactive jobs, and I will show you a few examples with RStudio or Jupyter Lab. And then in the future, I'll be talking about workflows, which is a way to submit a large number of jobs at the same time. And I will mention other submission techniques which are more advanced, and it's in the second group session, which is in 4 or 5 weeks. I don't know. Any question at this point? No, so let's start. The first part, you will learn how to create and submit a job, and how to monitor the jobs and monitor the queue, and how to control your jobs. The first things that you need to do if you want to submit a job is to make up your mind and think about what operations you need to perform. As I said earlier, a job is a set of operations. You need to make sure that you know exactly what operations you need to do in the job, because once you've submitted the job, it's very difficult to modify it. You have to cancel and submit again. And you need to decide which resources you need for those operations. For instance, like it's written there, 1 CPU core and 2 GB of memory for 1 hour. Yes.
Before submitting, check the process. I mean, in a debug level, or like we still don't know what the process exactly is. We shouldn't submit the job. We can just run the code like we do in local machines. And if it's working, then submit the job. That's the process.
So basically, it all depends on if you are able to work on a small version of the actual job. Then you can work on the front end and make sure that the whole process is correct before you submit a very large job. Because when you submit very large jobs, you will have to wait for the resource to get free. And then it's a pity if the job starts and then immediately stops because there is a typo at the first line of the script. So it's better to first test it on a smaller scale. And so the smaller scale can be your laptop, it can be the front end if it does not make perturbations for the other users. And I will be talking about this a bit later, but there are some clusters that have a special queue for test jobs where you cannot submit a large job, but you know that your job will be scheduled earlier than if you submit it to the main partition. So basically, you test on your laptop on the front end on the debug partition, and then you can use the main for the cluster. So once you know that the once you know the resources that you need and the operations you want to perform, you need to put them in a script. So it's typically a bash script, which you've learned how to write with Perry and Jerome a few days ago. And it has a specific structure. So just like any bash script, it starts with a shebang, and it accepts comments with a hashtag like here. So these are just for your own use. They are not interpreted by anything, except if they start with the hash and SBATCH. And this is the directive that you will use to give instructions or information to Slurm, to the job scheduler. And here what you see is that the first SBATCH line here, which is a bash command, but it's a Slurm of a command. You see it says, okay, the job name should be demo. And you will see that you can assign job names so that you can organize your work in an easy way. And then here the second one says, okay, I want the output to be written in this file. So you need here to realize that your program will not be running on your screen in a way. So it will be packaged by Slurm. It will be sent in a way to a compute node where it will run, and Slurm will capture all the output that the program would have written on the screen if it were on a classical computer, package everything, the output in a file, and then put the file in your home directory. And you get to choose what file name that would be. And here I chose res.txt. Okay, it's important to understand that you will not be sitting in front of the job, watching it perform its operations. It will be saved in the file. These are other parameters which describe resources with member CPU, for instance, here that indicates that the job requests 2 GB of memory per core. And this says, okay, I will only be using one task, and task has a specific meaning. In Slurm, you will see that in a few slides. But basically here it's requesting 1 CPU. And then you see here the operations with regular bash commands like echo that you've learned a bit earlier, which will normally write to the screen job starts at and then the output of the date command. But because it's running in the Slurm context, the result of this command will be written in this file. Okay, that's important to understand that. And then here you have another command, myprog, assuming I have a program that I've written myself, but stored in a bin directory. I run it with a data file here, for example, and I've prepended the line with srun. And srun is a piece of command from Slurm, and it creates what is called in Slurm a job step. And you will see more about job steps a bit later on. Things that you need to be aware of, because many people try this. In this part, you can use bash variables. So at some point, you might be tempted to have the name in some bash variables and hope that the name would be expanded here, but it will not be the case. For technical reasons, which are difficult to solve, but they don't allow bash variable in this. There are other ways of working which allow that if you need to read the script, but then again, this will be part of the other session. So important note, yes?
What if bash variable is defined indirectly?
That's the second point. So there are no bash commands allowed between the parameters. So basically, if you try to define the variable here, all this will be ignored. So as soon as Slurm sees a bash command, it ignores all the SBATCH. And this is a common mistake too. So make sure that you have the first part with the SBATCH directives and the second part with the actual commands. Now about srun. So there are two main things about srun. The first one is that srun will run this program on all the compute nodes of the allocation. So if you have only one node, it will run on one node. But if you have asked for 2 nodes, the srun command will run this program one time on each node. And actually, the number of times it will run the program this will become clear with the parallel job. But srun organizes the work across the compute nodes. That's the first thing. And the second thing is that doing that, it monitors in real time the memory consumption, the CPU consumption of the processes, and you can get access to them with the stat command. But again, you will see that later. Okay, so this is the structure of a typical submit script with the shebang. You can write commands. There are specific commands which are interpreted by Slurm, and then you have the job steps and the commands that you put in the job. Now that you've written the script, you need to submit it to the scheduler, so to Slurm. And the way you do that is with the SBATCH command. So when you are in the terminal, you have written with Vim, for instance, your submission script, you've saved it in a directory you know. Then you can run SBATCH and then the name of the script. What you see here is that I added one more parameter on the submission line. So you can give directives to Slurm in the submission script or in the submit command line. You can also pass the information by environment variables. So there are three ways to give parameters to Slurm: environment variables in the submission script or in the command line. And the parameters are taken into account in this order. So if there are parameters in the submission script, they are overwritten by parameters of the command line. And if there are parameters in the environment variables, they are overwritten by this one, and this one is overwritten by this one as well. Okay, so there are three places where you can give instruction to Slurm. It's important to realize that, and there's an order, so make sure that you keep the same order in your mind. Once you've submitted your job, either Slurm is happy with what's written in it, and then it gives you a job ID, or it gives you an error. But if it gives you, it responds with a job ID, it means that it has accepted the job, it's properly written, and the job has entered the queue, and it has been assigned a job ID. Yes?
What's the difference between the job ID and the job name that we specify in the parameters?
So the job name is what you decide, and the job ID is what Slurm decides.
And so we cannot look for a certain job by the job name, it has to be the job ID.
Actually, you can use the job ID when the job ID is discriminant.
Okay.
Because here you know that, sorry, you can look by job name if the job name is discriminant.
Okay.
The job ID will only be unique per job, but you can submit multiple jobs with the same name. And there are ways to manage multiple jobs with the same name as a whole. But the job ID will be always unique. And if you ask, no. Most of the comments rely on the job ID rather than on the job name. Job name is more for your own organization. So when the job enters the queue, you can see it with the squeue command. You might already notice that all the Slurm commands start with S. So we've seen SBATCH, srun, and here squeue. So squeue, this is the output of the man page. So if you type man squeue in the terminal, you will see the information about squeue. And it's important to realize that Slurm is a rapidly evolving program. So if you're looking for information about the commands, it's always best to look at the main page on the cluster, then looking on the information on the website, because the information on the website is always about the latest available Slurm version, and we don't update Slurm every so often. So it's important to make sure that you're reading the documentation that is about the Slurm version that is installed. So squeue, how does it work? It's like this. So if I type squeue on a cluster, you will see multiple columns with job ID, partition, name, and so on. So the job ID, you understand already, it's the job ID that was assigned by Slurm when you submitted a job. And then you have the partition. And the partition is a logical partitioning of the nodes. So the nodes are organized in partitions. Here, in this example, you have two partitions, one named batch and one named debug. And so the partition can have either different hardware or different policies depending on the clusters. For instance, on the Metropole, there are no partition at all. But so what you need to remember is it's just a set of nodes. And here it shows the name, and you see here two jobs that have the same name. The user who submitted the job, so DFR is me, DBR is Bernard, and ST is a state. So what you will most of it's a fake, Bernard. I see your row, it's just made up. So the state is the, most of the time you will see two states, either your job is pending within here as PD, or it will be running. So if it's pending, it means it has entered the queue, but it's still waiting for the resources. If it's running, then the resources has been allocated to them. The script has started, and your program should do its work. There are other states, but these are the most frequent ones. Then you have the time, the running time of your job, for how long your job has started. It's important to understand that you need to specify a maximum time for your job, and your job must be completed within this time frame to organize the turnover of the jobs. And then here you see the nodes column, which is the number of nodes that you have requested and that have been allocated to your job. And the node list is the list of nodes which were allocated to your job if the job is running. Otherwise, if the job is not running, it lists the reason why it's not running. And here, again, two main reasons: either resources, meaning that your job is the next one to start as soon as the resources are free, or priority, which means that actually there are other jobs with higher priority that will start before your job, and you still have to wait for those jobs to complete. When you see something like this, it actually means this. So nodes with interval here is the set of nodes which are named like this. So it's a shorthand notation for a set of nodes. The squeue command accepts parameters to either filter lines or filter columns, or also to choose columns. For instance, something that we'll use a lot is squeue-me, and it will only list the jobs which belong to you. So if I run this, I see only both my jobs, and I don't see Bernard's jobs anymore. Often used with --start, which you see modifies the columns which are shown in the screen, and adds a column with the start time, which is an estimation by Slurm based on its current computation of how far in the future your job is supposed to start. Be aware that this is not a promise at all. So it's the current state of the cluster. So if someone with higher priority submits a job after you've read this, this could evolve. This time could evolve in the future. Here you see an example where you can choose a partition that you are looking at, or here an example with -- format where you can actually choose exactly which columns you want squeue to show, and you can combine all the arguments together. Any question about squeue? A lot of information. I hope you're not overdrawn. Here, even more information. So if you want to know everything about the job, everything that Slurm knows about your job, you can use the scontrol show. Again, Slurm command starts with an scontrol show, and then you give it the job ID, and it will output all the information that it knows about Slurm. So when you have issues with the job, the first thing that we do is run this command to see exactly what you requested, what Slurm allocated on which node, and so on. Now, imagine that you have submitted a job and you realize that you made a mistake afterwards. You can use the scancel command. And the scancel, again, starts with the S and then cancel. You understand what it does. Simply, you give it a job ID and it cancels the job. Example here, I run scancel with this job ID, and afterwards I only have one job running. And you see the scancel has a lot of options that you can use to target multiple jobs at once. So if you use scancel --user equals and then your username, it cancels all your jobs. Yes.
Can you cancel the job of somebody else?
You can try.
Possible?
Yeah, because if you are in a hurry, of course it's easy. You can cancel someone else's jobs and your job will go.
No way.
I'm asking you just a bit of patience and you will see. Yes?
Is it better using scancel kill?
Sorry? Using?
Do you recommend using, for example, kill to kill a job, or it's better using scancel?
It's a good question. Actually, you cannot use kill to kill a job because the job is running on another computer. So what a scancel does is run kill for you on the correct job, on the correct processes. But scancels accept mostly the same options as kill. And Olivier will show you that in the tip pointing session, which is just after this.
No, this is afternoon.
As I said.
After this
Afternoon.
one.
Sorry. Yes?
Can I include my email information to receive the updates about the job?
Yeah, you will see that in the slides. It's basically a Slurm parameter. So you put it either in the script or in the command line or in the environment variable. But there are examples you will see in slides. If the error that you made does not require you to cancel your job, but you would like to modify it, you can do it if your job is still pending. Actually, there are some parameters that you can change while the job is running, but most of them are frozen once the resources have been allocated. But if the job is pending, you can use the scontrol update. You give it a job ID, and then one of the features that you want to modify, for instance, here, the number of nodes, and I can modify while the job is in the waiting area, the number of nodes, so that it goes from 2 initially to 3 after I have modified the job. Of course, it changes the system in the way the priorities are computed and so on. So if you have seen that your job is supposed to start in 10 minutes, and then you multiply by 10 the resources that you request, it will not start in 10 minutes unless you have a lot of luck. Okay. Yes?
What is the best way to choose the number of nodes?
In the next slide. Because it's a very good question. So, and actually, in this part, any question about the first part? So the basic ideas? No. In the second part, we'll see how to discover cluster features. Slurm will give you all the tools to understand what a cluster can offer you in terms of features of resources. You will see how to target specific resources and how to choose suitable values for the memory, for the time, for the number of nodes, for the number of CPUs. And you will see also, very important, how to get the actual usage of the resource by your job. So it's important when you submit a job, you ask for 10 nodes, then your job is completed. You look into the accounting, you will see that it only has used 1 node, then you need to change something in your script because there are resources that you have been requesting, being allocated, that you are not using. So the Slurm command to get the info about the cluster is called sinfo. If you run it on a cluster, you will see something like this. Again, organized by partition. You see the state of the partition, which can be up most of the time or down if there is a cluster maintenance. You see also per partition the time limit. It's important to realize that there is a time limit on the clusters. So you cannot run forever on a compute node. You have to make sure that your job runs within this time limit. And you see here the state of the nodes, which can be idle, so there's a node doing nothing, or alloc, meaning the node is completely allocated to a job. or mixed, which is a job that is not entirely allocated to a job, so there are still resources available there. If you run the sinfo on a CÉCI cluster or UCI cluster, actually, it might look different because we have wrapped this with more colors and more information. But if you run the sinfo with command before, so if you write command sinfo, you will get exactly this. The sinfo command, just like the squeue command, allows you to choose the columns that are displayed. But here it's a format string. For those of you who know about C or Python, there are also format strings for Tron2. So every character behind a person sign has a specific meaning that which you can look up in the documentation. But here is an example where I write the number of nodes in the partitions, the available features, number of CPU per node, memory per node, and number of GRS. And GRS is the generic resources, among which you will find the GPUs for those of you who need GPUs. What I wanted to draw your attention to is the avail features column here. So most of the clusters are homogeneous, meaning that every node is exactly the same as every other node. But there are clusters with hardware which are different from one node to another node. And so we tend to label those nodes with a specific feature. And here, for instance, you see AMD, ROM, these numbers, and virtual. All these are features of the CPU. And if you run it, if you run this command on the Metro 4, you will see that every node is identical on Metro 4. But on Hercules, you will see that there are different types of nodes with different CPUs, different amounts of memory. And all this can be shown by the sinfo command. Just a few words about QoSs and licenses to be complete. A QoS is a quality of service. So on the clusters, we can define quality of services to give more privileges for a short amount of time to some jobs. For instance, here you see a QoS called priority, which gives a 10,000 boost in priority for a job. And we use that sometimes to help people submit jobs in an easier way. Most of the time, a QoS that boosts priorities gives a shorter limit on something else. So typically, we can boost priority for shorter jobs. But then the QoS means that your job cannot be as long as the partition would allow if you were not using the QoS. And licenses are not much used here, but it's a way to manage the set of licenses for software which is not free on a cluster. The way you target those resources is with the SBATCH command, the SBATCH parameters. So if you're looking for a specific feature, the corresponding parameter is called SBATCH. If you need to use a specific generic resource, you can use either --GRS or --GPU. You will see examples. Access a license is with --license. Choose a partition is with --partition. Choose a QoS is with --QoS. And then the options here allow you to choose the amount of compute resources in terms of nodes, number of tasks per node, and CPU per task. And this will become clear in a later stage. And then other examples with job name again. You can write some comments. If you want to remember what the job is about, you can attach a comment to the job when you submit it. And then in the squeue, you can request to display the comment column so that you can see the comment that you've written. There was a question about the emails. This is how you do it. You specify that -mail type, and then you can ask to have an email at the beginning of the job, at the end of the job, only if it failed at all situations, or at 90% of its time limit. So it's sometimes convenient to be warned that a job is about to be killed, because it can help you decide about what to do for the job. And then you need to specify your email address. So the system does not know exactly who which email you want the email sent. It's important not to have typos, please, because for every email that Slurm sends on your behalf with a typo, we get an email. And sometimes when there are a lot of people who make mistakes in their emails at the same time, the email servers from the universities can ban one another. So it has already happened in the past. So it's important to make sure that you don't have typos in there. You can use -- only with the SBATCH. Yes.
About the mail, what is real time? Okay. Like, I guess it is the frequency of sending the email, right?
Which one?
Mail time.
No, it must be either begin, end, or fail, or this. And if you put begin, it will mean you will only get an email at the start of the job. If you put only end, it will be only an email at the end of the job. If you put fail, it will only be an email at the end of the job if the job failed. And then all, it will be all this. And time limit is 90% of the time limit.
So
You can
meaning that
combine them.
it is mandatory to specify both parameters.
Yes. Yes.
So the time limit is 2 days, right?
The maximum time limit for the job is 2 days, but the time limit for your job is what you specify in your submission script.
Okay, so it's 2 days to run the job.
No, you can ask up to 2 days.
Ah, you cannot ask for more.
No, you cannot ask for more.
And if you need more, Olivier will explain. You need patience.
What so much advertising for me.
It's SBATCH and then mail type something.
So if you want to include this parameter in the submission script, you will write #SBATCH in capital letters, and then exactly this. If you want to include it on the command line, we'll run SBATCH in lowercase, and then this exactly, and then the name of the script.
And for taking the email name, it's another kind.
Yes. So these are two different comments, but actually you could put them both on the same line. It doesn't matter. Yes?
I don't finish in 2 days. Can I stop and apply?
This afternoon.
Olivier will explain that. It's not magic, it will not work automatically, but there are ways to do that. Okay, but it's the subject of the checkpointing session this afternoon. And then lastly, you can submit multiple jobs with dependencies between them. So if you submit the first job and you have another set of operations to do only when that job is finished. So typically you have pre-processing of some data, analysis of the data, and then post-processing of the data, or you have generation of the data, then post-processing of the data. You can submit both jobs or all 3 jobs at the same time, but with an ordering that makes sure that the second one will start only if the first one has completed correctly. And with that, you can build a whole set of dependencies between jobs. And we will see further techniques this afternoon in the workflow session. Any question about this? Yes.
I don't understand what you use when system opens for Requeuing.
Sorry. Yes. So I said that you got to choose the name of the file where the results that will have been displayed on the screen should be written. And here you specify that the output, so actually what will be sent to std out, if you remember the bash session, will be put in a file called result, and then this is a placeholder with for the job ID. So actually what Slurm will do is take this, replace the %j by the job ID, and use that as a file name. And this is exactly the same thing, but for the standard error. If you remember the distinction between standard output and standard error, you can specify 2 different files. If you don't specify this one, everything will be merged together and sent to this one. So it depends on what you prefer. Sometimes it's easier to isolate errors and warnings in the different files. Sometimes you want everything in the same file. It's up to you. Yes?
It's about the dependency. So, for example, with the job ID, for example, write directly dependency and dependency or
No, so
after and
yes. So you need to write that dependency equals, and then either after OK or after not OK or after any. And then column, and then one or multiple job IDs. So you can have a job that depends on the fact that another job has after OK as I don't remember if it's finished or started. Yes, no,
finished.
after just after is after it started, after OK is after it finished OK, after not OK is after it failed, and after any is after it failed or completed. But we'll see this on further slides. No more questions? Yes.
I remember the percentage G is the job name or job ID?
ID. Actually, if you want the job name, you can put a capital letter here, capital J, and it will be the job name. But if you use a job name, then it's your responsibility to make sure that there are no two jobs with the same job names. Otherwise, it will erase, unless you use a special mode which is called append, which Olivier will explain. So if you want to play along, you can connect to SSH, you can SSH to limit 4 and run the game shell called Slurm. You will be in the familiar environment of the game shells, and you will see the missions. Just a reminder that you run GSH goal to see the goal of the mission. You do what it needs, and then you run GSH check to check if the mission was completed. And if you don't know what is happening and you have the feeling that the job is broken, you can run GSH reset to restart the mission from a clean state. Okay, I'd like to resume the slides. You can still play in a few minutes. I'll make a break and then you can finish the game if you want, or if you still need more time, you can have a look at the game later on. So I don't know if some of you have reached that mission, but there was a mission about killing other people's jobs. Has anyone succeeded? Okay. Has anyone who has not root access to the cluster succeeded? No, so actually when you try to kill someone else's job, you have a message saying that you are not root. Okay. I would like to specify a few words about limits. So there are two kinds of limits on the clusters: the natural limits, which are dictated by the hardware. So if a computer has 500 gigabytes of memory, you can not run a job that requires 700 gigabytes of memory on the job. You understand that? And there are admin-defined limits. And when we as admins define limits, it's always to make sure that everyone has a fair access to the cluster. Okay, and especially the maximum time that is defined on the cluster is to make sure that everyone has a fair access to the cluster and there is no one sitting actually on a compute node and using it forever. You can view limits with sactmgr, which is a slurm command. Again, as it's a slurm command, it starts with an S. And actually, you will see that limits can be set on multiple aspects of a job. The number of jobs that you are able to submit or that you can have running at the same time, the size of the job, the duration of the job, the CPU usage among a group of users, and so on. And the limits can be set either for the whole cluster or for a specific user or for a group of users or for a specific partition or for a specific QoS. And all this you can discover with the sactmgr. So it's S for Slurm, act for counting, and mgr for manager. And so here, for example, I run on NIC5 the command sactmgr list user, and $user is my username, with a sock and then the list of columns that I want, and I have here all information about those. You can see that there's a QoS called normal, and the QoS normal has a limit on the number of CPU that can be used by user per user. will not explain this further. It's just to show you that there is a way for you to discover the limits on the cluster, and it mainly is with the exactmgr command. And if you really want to delve into the details, we have a page in the documentation that explains that in very much details. So when you submit a job to the cluster, most of the time it will be sitting in the queue. And there are multiple reasons why it could sit in the queue. You've seen the priority reason and you've seen the resources reason, which are easy to understand, but there are many other reasons which are listed here. And if you want to know exactly what those reasons mean, you can have a look at this page in the documentation. So again, I'm not going to explain everything. Just know that if you see something which is not a priority or not resources, it's always interesting to have a look at the documentation, make sure what is the reason, see if you can understand the reason, and it might be something that you need to change in your job. So for instance, partition node limit is a job that will never start because it tries to use more nodes than the limit on the partition allows, while this job will start as soon as the dependency is met, and so on. So have a look at those words and have a look at the documentation about what they mean. Yes?
The required node not available. I was just wondering, like, is that?
So here it happens when in a submission script you specify you want one specific node or a specific configuration of nodes, and there is no node that fulfills that configuration, or the node that you targeted is not available. So either you wrote -- node list equal and then the name of the node, and it happens that that node is down for some reason, or you specify that you want 5 GPUs, for instance, and there are no nodes with 5 GPUs in the cluster.
That's probably going to be in our decision making for how to,
yes,
what to ask for in the case that we ask for a question.
Yeah.
I don't know if you already found this, but this is the list of my stuff, like the personal jobs, or is the all jobs in the.
So if you run squeue with --me, it's all your jobs. If you don't put --me, it's the host. And by the way, there was a question about that. The game you are playing in game shell is actually on the cluster. So the queue that you see is the actual queue of the for cluster. So it's not a made-up environment. A few words about resource requests. It was asked previously. How do we choose the number of CPUs? How do we choose the number of nodes? How do we choose memory, and for how long? The issue is that you need to find a trade-off between the time your job runs and the time your job waits for resources. So the more resources you request, the faster your job should be able to run, but the longer probably it will have to wait in the queue for those resources to be freed. And so the actual time to solution, so the time to science, as we call it, is the sum of the waiting time and the running time. And you see there is a sweet spot. If you mentally add those two graphs, there's a sweet spot somewhere. The thing is, it's not easy to find. But the more resources you request, the faster your job could go. Not necessarily the case. It all depends on what we call scaling, and you will see this in the parallel computing course. And the more you also have to wait in the queue. So yes.
So you let that occur just naturally based on what users are doing, or do you prefer that we get in and out quick, or that we share the resources?
Sorry, I didn't catch the first part.
So this trade-off that you're describing there is essentially for us to decide what to ask for so that we can get it done sooner. But in terms of the resources available, I suppose there would be two different strategies to get everything done in a certain amount of time. And if we get everything done quick with a lot of resources, or if we share the nodes, what do you guys prefer that we're doing here?
It depends on the clusters and on the policies of the clusters. So if you have a clusters with a very short maximum allowed time, it means that we encourage you to request a large amount of memory for short times.
Okay, so you're doing this already.
And so on limit 4, for instance, we like to have very large jobs, but quite short. And on Hercules, or Dragon, they allow very long job, but for only 1 node, for instance. It depends on the policies of the cluster. And that's why we are sharing the clusters, because we have different hardware and different policies. So a practical approach to know how much CPU and memory you should request for a job is to run a smaller size version of your program on either the front end or your laptop, and run the top command. And the top command will show you all the processes that are running on the machine. And for each process, it will show you the user. So you should have a look at your processes. And the two important elements are RES here, the residence set size. So it's the actual memory that the process is using in megabytes, and %CPU here. So %CPU is the percentage of one CPU that your program is using. So if you see here that your program is using half a CPU, it means that the limiting factor is not the CPU, and so there is no reason to add more CPUs to your job. While if you see here that the percentage of CPU is going above 100%, it means that your program is able to use multiple CPUs at the same time. So in your submission script, you should request multiple CPUs. So the top command for the job in real time, you can have a look to get an idea of how much memory it's consuming and how close to 100 or above percentage of CPU your program is using. It's not always easy to run a small size. Yeah, of course, if you run that on a smaller version of your program, then you need to extrapolate to the actual size of the problem to get the actual values. Sometimes it's not practical, and it's easier to get the actual values for the actual job. So what you can do is submit the job with very large resource requests the first time, and run your program with a time command. Here, it's important to know that it's not the time bash command, it's a time Unix executable. There was a question about that earlier. You need to write user bin time here, not just time. And time is another command. And it has the same name, but it's a distinct command. And this one, with a full name like this, with the -- verbose option, gives you much more information than just the time. And you see here the user time, system time, and most importantly, the percentage of CPU this job got. So it's the same information as the top command, but average over the duration of the process. And here you see the maximum size. Again, the maximum amount of memory that your program is used during its course of action. So the pragmatic approach is to use guesstimates for the first job. So very tight limits. You take 2 or 3 times what you think you would need to submit a job, and then you analyze the accounting information, either the one that you got from the time command or the one that you can use from the stat command. If you remember, I said earlier that the command in a job script that is started with srun will be monitored specifically, and you can ask stat the amount of memory and so on that is used by a specific command in your submission script. So the exact man page looks like this, and the output looks like this. If you specify the format here, again, like most of the Slurm commands, you can specify which columns you want to see in the output. You will see for one specific job, multiple steps. So steps that have a numerical component after the dot are the steps that you have started by yourself using the srun command. So if you remember in the mission, there was a srun sleep, srun hostname, and so on. Every srun will appear here. These are internal steps for Slurm's working, but these one are the one that you have created. And for each of the steps, you see the requested memory and the memory used, and you can compare both numbers. You see the time limit and the elapsed time, and again you can compare these numbers. And you see here the CPU time, which is the number of CPUs that you requested multiplied by the time that you requested for them for, and you can compare that to total CPU, which is the integral of the CPU usage over the course of the job. Okay, and so this number should be as close as possible as to this number, same here and same here. Same somewhere there. Okay, no, it's correct. So this is a point, not a column. So this compared to this, the format is not the same. So you need to use your brain to compare. My brains are a bit lazy at the moment. Okay, so you submit a job, you observe the resource requests compared to the actual resource usage, and you take action. So if you see that the request memory is 10 times what the job has requested, maybe you can divide the request by 7 or 8. Keep a margin of security, because if you go above that, as you've seen in the mission, your job will be constrained, and most of the time will crash. If you want really detailed information, you can get that on some clusters with the -- profile option of Slurm. But you need to see with scontrol show config, which is a command that shows you the configuration of the cluster. So if you want to know everything about how the cluster is configured, you can get that from scontrol show config, and you will get all the parameters. And one of the parameters is the act gather profile type. And if it's not empty and it's HDF file, actually you can request from Slurm an HDF file with all the information in terms of memory usage and CPU usage over time for every task in your program. And you get a file, which is an HDF file. You will have a specific session about HDF files in the future. But basically, it's a set of time series. So you have one time series per node, per CPU per node, and per memory and everything that you want to measure. So you can have a look at the time series and see if your job is using memory for a long period or just a short peak at the beginning, which can happen a lot, and then not using in the past. And if you see that the usage is not homogeneous over time, maybe you can think about cutting your job in pieces to not request too much memory if it's not used, and so on. And the best approach is to use profiling tools. And profiling tools is also the topic of a training session by Bernard in a few weeks. Any question about this? So, yes?
Regarding cut my job in different parts.
Yes.
This means that I need to experience how in each part my job is get a fix in the consummation of the memory, and then based on this define where I need to cut.
Yeah, so there's an easy situation, for instance, is if in your job you have one program that runs and then the second program that runs after, and you realize that the first program uses a lot of memory but not much CPU, and the second one uses not much memory but a lot of CPU, then you can split those programs into two different jobs. Okay. Now, if you have a single program that has that behavior of using a lot of memory for a short time, and then either if you are the developer of that program, then you can think about writing everything in a way that you can split the code into two different executables. If you're not, then it's much more difficult And then you could use the techniques that Olivier will show in the checkpointing session. But most of the time, it will be a very large effort to do that if you're not the developer or if the job is not already split into logical sequences. So if it's a single program that you're not a developer of, most of the time, there's nothing you can do. And actually, you could free resources during the course of action of a job, but it's a complicated process. But if you're motivated, you can write your submission script in a way that after some period, it yields some resources back to the schedule, and it shrinks the job. But it's a very advanced mechanism. Yes. No, just for your job. Yeah. The whole system, we do that. We check how the memory is used and how the CPU is used. And sometimes you will get an email from an admin saying, okay, your job is requesting that amount of memory, but using only this amount, so please have a look. Because we monitor the overall health of the system, but these tools are for your job and your program. And actually, these tools will not only tell you how much memory it's using, but where in the code the memory is used the most, or where in the code the CPU is used the most.
Is it something that is installed on the clusters?
Yes. It could be June, but it's Bernard, the specialist. So in the game maybe you've seen that at some point it was about tasks and add task and CPU per task and so on. This part will explain what this is. Because we will start learning how to write submission script for parallel jobs, because the main power of the clusters lies in the fact that there are multiple nodes with multiple CPUs in there. And actually, one individual CPU, so one individual compute unit on the cluster, is often less powerful than what you have in your laptops. Because in your laptop, you have 4, maybe 8 CPUs, and they can run at a higher frequency. So they are faster than what we have on the cluster. But in the clusters, for instance, the Metro 4, we have 128 CPUs per node. So the interest for you as a user of the clusters is really the parallelism that you can get from using multiple nodes and multiple cores at the same time. It's what I just said here. So parallel jobs is what you need to run on the clusters, and there are multiple ways to run parallel jobs. We'll talk about shared memory jobs, distributed memory jobs, accelerators, and embarrassingly parallel jobs as 4 distinct workloads that are using multiple CPUs on the same cluster to perform quick computations. The type of parallel jobs that you will need to start will depend on the software that you are using. So if you are the author of the software, you know how it's organized, so you know that it can or it cannot use multiple nodes in parallel, for instance. If you're not the author, you really need to look into the documentation about what your program is able to do, so as to make sure that you request the resources that your program will be able to use during the job. First, to talk about the parallel usage of the clusters, I need to explain a bit how parallelism can happen in the operating system. So, as a reminder, if you have a program, most of the time it comes from a source code, which is a text file with instructions, and this text file is compiled into a binary version called, let's say, program.exe, and then this program can be started when you type its name on the command line. For instance, there's a small program called the loader that will take the code, the compiled version, put it in memory, and start the execution thread. And so inside the internal structures of the operating system, one process, so one running instance of your program, has some data, some files open, and a thread of code, which is a sequence of the instructions that you have written in the file and that have been compiled. And And then what you have is a process running in memory with a process ID. So it's important here to distinguish between a process ID and a job ID. So the job ID is the job in a context. So the Slurm queue and the process ID is the ID of the running program inside the operating system on the cluster, on the node on which that program runs. When you do that, you have a single thread of execution, and it only requires one CPU. But Slurm makes sure that this thread has access to one CPU for the whole duration of its lifetime. So what you can do if you have multiple CPUs is run the same executables multiple times by calling the loader multiple times. And you end up in memory with multiple instances of the program, which each can use a single CPU if you have requested one CPU for each of them. So you have multiple running instances that can work in parallel using different resources. So this is what you can do if you have one program that is not able to run in parallel, but you can start multiple instances of it. Of course, if your program is not aware of this behavior and does the same thing 3 times, there's no point in doing that. But you can write your program in a way that even if it started multiple times, it will do different jobs, different tasks. Another option is to insert inside the code of the program the instructions to tell the program to spawn itself, spawn a sibling, to split itself into, for instance. So the small program in there is a program that if you compile it to a compiler, you get an executable, and if you run this executable once, you actually get 2 processes in the data structures of the operating system on the computer. And those 2 processes are linked with a parent-child link, which has specific implications in the way they can communicate on the node, and they can communicate with a set of tools or technologies that are called together inter-process communication. It's important to realize that if you have one program that runs like this, it can use 2 CPUs, but only on the same node. So you will not be able to take this process, put it on one node, and this process on another node. So it's important to realize if the processes are able to communicate over the network through the nodes, or if they are only able to communicate over the memory on a single node. There's another way of doing that using other tools, and it's called multi-threaded code. And what happens is in the same process, you can have multiple threads of execution. And this thread can access each of them one CPU. So you can have your program that has multiple threads of execution to work in parallel. For instance, with OpenMP, it's one of the topics of the sessions in the parallel programming block. And finally, if you have the same as before in the first example, a single thread program that you compile it and you run it not with the basic loader of the operating system, but with srun, then srun will start as many instances as you have requested in your job submission script. So here is the same idea as before. The first example where I said if you run the program multiple times, you will have multiple instances of the program in the memory. Here, with srun, actually the program will be started on as many nodes and as many CPUs that you have requested in the submission script. So if you requested 4 nodes and 20 tasks per node, it will be started 20 times on each of the 4 nodes. But here I anticipate. So actually, a multiple node job like this is possible if and only if either they are all independent. So imagine that you write a program that does some Monte Carlo analysis, and there's a random step in there, making sure that that has the consequence that when you run it twice, you get different results and you can aggregate the results. So then it's very easy to run it multiple times on the cluster, and then at the second stage, to gather all the results. But it's not the only way you can work. Some processes can work in a what we call embarrassingly parallel fashion. This is, or if you are able to have your program communicate with other instances of itself through the disk, for instance, there are software that work by sharing a common database, and they organize the information transfer from one instance on a node to another instance on a node through the database. Then you can do that. Most of the time it would be in a master-slave setup. Or you can, third type of multi-node process, run the processes on multiple nodes and have them interact through the network directly. And so on the CÉCI clusters, there are clusters which are really meant for that type of workload. They have a network that is very, very fast. And so you are encouraged to do that kind of workload on those clusters, like Lemaitre 4 on X5. By contrast, Dragon and Hercules do not have such a fast network, so there you are mostly stuck with either this type of parallel job or this type of job. This mostly uses MPI, which is one of the libraries that is described in the parallel programming session. So these are the building blocks that you will use to create a parallel job. A parallel job typically comprises a sequence of steps. So you remember that a step is created with the srun command, and each step can start multiple tasks that can be either running in parallel or in sequence, and each task can use multiple CPUs at the same time. Okay, you see there are steps, multiple steps in the job. Each step can comprise multiple tasks that can run either in parallel or in sequence, or part of them in parallel, part of them in sequence, and each task can use multiple CPUs in parallel. You will see, so this will allow you to do a lot of things, but you need to get your ideas clear in there. To try to make it clearer, so if you have this situation or this situation, so if you remember, this one is a situation where you have a multi-threaded code written, for instance, with OpenMP. So actually, you have one process that can use multiple CPUs with multiple threads. Or if you have multiple processes that are working together and communicating through inter-process communication, was the second example, then you need to request CPUs on the same node. And how you do that is simply using -CPU per task equal n, the number of CPUs that you need. For instance, here you would request 3, here 3 as well. And the number of tasks is implicit, it is 1. Simply because you have one task here, you can see each task as a process. And here you still have 3 processes, but as they are interconnected through inter-process communication, they should be seen as a single task in Slurm. So this is how you would write it. You see here, I kept it minimal just to focus on the main point. And this example is available on the CÉCI clusters in the central storage. So on any CÉCI cluster, if you go to /CÉCI in capital /proj /training/Slurm, you will see the examples here, and they are auto-contained, so you can just copy them and run them. And what you see here, second line is modulo GCC, and then I compile this program, which is a hello world written in OpenMP, and again, OpenMP is the topic of another session. And then here I simply run it. So what you need to remember is, if you see in the documentation of your software that it's multi-threaded, you need to use this constraint to choose the number of CPU. Typically, if you are using MKL or OpenBLAS or Python multiprocessing or RDuMC or TBB in C++, those all need to work like this. Another option is to request a full node, and you do that by using the --exclusive. option in Slurm. So if you request one node and dash dash exclusive, it means that you want a full node independently of the size of the node. You just want a full node. One important thing is that you need to specify the memory as 0. And that would mean not 0, but the actual amount of memory available on the node. And if you don't put it, you will get the default memory per CPU that is configured on the cluster, which might not be the full memory of the node. So if you request simply a full node with dash dash nodes for 1 and dash dash exclusive, you could get your job killed because of a memory overconsumption, even though there are no other jobs that could have been able to use the memory. Just make sure to use both at the same time, dash dash exclusive and dash dash memory equals 0. Now, if you have a program that is based on MPI, as you read in the documentation, and it's able to use multiple nodes at the same time, then you will start with dash dash and tasks equals, and then the number of tasks that you want to start. So for instance, here I have 4 instances, 4 processes, each being a single task. And so I use SBATCH dash dash and tasks equal 4. And here again, I have an example with MPI compiling the executable. You will see that in the compiling session, in the MPI session. Here, what I wanted to see is that srun can be used to start an MPI program, and srun will take care of distributing all the process to all the nodes that were allocated to your job. If you read the MPI documentation, it would say that you need to use MPI run to do that, but actually MPI run uses srun behind the scenes, so you can use both. They have different options for different objectives. So sometimes you will prefer to use this one, sometimes you will prefer to use this one. That depends really on what you want to be able to do in the job. Yes.
So for example, if I have a program that allows, for example, to manipulate 10 files, I want to run, for example, a process for each file. That one?
No.
It is the previous one, or
you will see it in a few slides. But basically, you are more in this type of example. If the images are really independent, it depends on how long the processing goes. But that is more the topic of the second Slurm session. I will try to keep it understandable for this moment. So where was I? Here is another example. Here is another example with MPI, where I ask exactly the same thing and tasks equal 4, but for some reason Slurm allocated 2 on the same 2 on 2 nodes. So if you request 4 tasks, you can either have 4 tasks on the same node, 1 task on each of 4 nodes, or any combination that leads to having 4 tasks, if you don't specify anything.
How we can
most of the time, your jobs will be very similar one to another. If you're in a application domain and you have a single program that you use, you will need a small amount of time to understand which framework you need to insert the job in. But then most of the time it will never change, and you will just reuse and adapt your submission script from one job to another. So it's not something that you need to do at every job. But the first time you run a new program, you need to ask yourself those questions. And yes, so this is another example. If I ask for n task equal 4 without specifying anything more, I can end up in this situation. Most of the time, you will not care. but there are some workloads where you want to specify specifically how the processes are distributed among the nodes, and you can do that with the end task per node and nodes and tasks. If you combine them, you can decide between having all the tasks spread across the maximum number of nodes, or at the contrary, condensed on a single node, if it's possible. I'll let you read this, but you can decide between two extremes. Yes?
I'm not sure if it's that understand. There is some, I'm kind of lost in all information. There is some questions that you should ask before submitting them.
Yeah.
So one of them is how much CPU do I have? How many nodes do I need? Or how many memory do I need? Like this. And for checking all these things, we're right now talking about how we can define these things. But before we were talking about how we can understand how many CPU. Like, I'm just repeating because I wanted to show that that is the plan, or this is what we should reach.
Yeah. So at the very end, I have a question, a guide with many questions, and if you have an answer for each of the question, it will lead naturally to the corresponding submission script. But indeed, what you need to do first is know the program that you are using. So you need to read its documentation or ask your colleagues if they have read it to see if it's able to do multiple nodes, or if it's able to use GPUs, or if it's able to, or if it's not able at all to do parallel computing. And this is one information that leads you to using one of those examples. And then that being said, it will not change over the course of the multiple jobs, but each job might need a larger amount of memories or smaller amount of memories. So then you will adapt not the structure of the submission script, but the value that you put in the parameters based. And if you need to read a file that is 1 gigabyte large, it's different if the previous job was reading a file for the same purpose that was 1 megabyte large. You know that you need more memory, and so you adapt in consequence. But the way the tasks are distributed will not change. Does that make sense?
When you say you know how much memory that need, it's for me, the answer is I don't know.
Yeah. So what I was just saying now is about if you are reading a file, you can see the size of the file with the ls command, and you know that the memory that would be needed is at least that amount. Okay, so you have a lower bound. And it's not always easy to understand how much memory one program used, and that's why what you can use is the profiling tools, or use the accounting to see how much the similar program has used in the past, so that you are able to project what you will need in the future job. But it's not a perfect science. Sorry, I need to go a bit faster. This is another construct in Slurm to start multiple processes which are different in nature. If you remember earlier, I talked about master-slave setups. If you have a master-slave setup, so one program that organizes the work and multiple other programs that actually do the work, you will do that with this kind of construct. You need to write in a file which program will be started for each task. So here I request 3 tasks, and I say task 0 will start this program, and task 1 and 2 will start this program. And these programs are written in a way that they coordinate through the coordinator to decide what work they do. So if you are using MATLAB, for instance, multiple MATLAB programs work in this setup. If you have a program that starts slaves or workers, it's this kind of setup that you need to use. And finally, if you need to use GPUs, you have 2 ways of requesting GPUs, with either --GPUs or --GRES equal GPU, because GPU is a kind of GRES. GRES is a generic resource. if you request n GPUs, you will get n GPUs independently of the number of nodes that you have. But if you request gres, they are requested per node. So if you request one GPU and one node, you get one GPU. But if you request here one GPU and two nodes, in total you get two GPUs. Okay. While here, if you request two GPUs and don't specify anything else, you could end up with two GPUs on the same node or two GPUs on two different nodes. And then all of these options, to make things simpler, you can combine them. So if your program is able at the same time to do multi-threading processing and communicate to the network, well, you simply add the two options corresponding to the two cases. Okay. So that again, you need to look at the documentation of your program to see if it's able to do multi-threading, if it's able to do message passing or MPI, and so on. We were talking about working on multiple images, for instance, in the past. So this typically would be done with a job array. So a job array is a construct in Slurm where you create a submission script corresponding to one image, for instance, and then you tell Slurm, actually, I have multiple jobs exactly the same, except for some parameter, and you, in one SBATCH command, you submit multiple jobs. So here with SBATCH and this submission script that has this dash array equals 1 to 4. When I submit it, you see that squeue will tell me that I have this job ID, and there is a range here saying that actually this job is made of 4 independent jobs that will be scheduled independently, and in them the Slurm array task ID variable will be defined with different values. So there are examples in the second section on how to do that, but basically you would use a value in this variable to decide on which file you are working for a specific job. And so if you have 4 files named image 1, image 2, image 3, and image 0, you can use a construct like this to here put image and then this environment variables, and that specific job inside the job array will take care of that specific file. So it's a way to, in a single script, create multiple jobs which are independent. So if you cancel one, it will not impact others, but you can also work on them as a group. So this is the reference of the group, and the reference of a single job in there is this underscore and then the task array here. And you can cancel the whole group at once or single individual in the array. You can also specify job dependencies with that dependency. You see here a specific example after OK and then some job ID. And I've mentioned this earlier, so I won't spend more time on this. Do you have questions on this part? A lot of information, but and I split the session in two. Like last year, it was.
So, for example, after OK, you need to know the job ID, but if you have multiple tasks,
yeah, it's a pity.
After,
yeah.
Is there a way to?
Yeah, and you will see that in the workflow session this afternoon. Be patient. But thank you for it. Any other question? Okay, briefly, I mentioned interactive jobs. Just I will give you recipes here about interactive jobs. So jobs where you don't want Slurm to run your job blindly on a node and write everything in a file and then give you the file afterwards. You actually want to see the result or want to be able to run the programs by the commands by yourself. The typical command to do that is salloc. It works exactly as SBATCH. So you can request ntask equals something or nnode equals something, and it creates an allocation, but it does not start any program. And then you can start the program by yourself. So here is an example. I loaded some modules, and then I run. Where is it? So here, salloc. You see that it tells me that I have a pending job allocation. So this will wait until you have resources available for your job. By contrast with the SBATCH command, the SBATCH command gives you immediately the answer that your job ID is something, and then you can keep on working afterwards. Here, when you run the salloc command, it will freeze until you get resources allocated to your job. When the resources are allocated, you see here the startup process of the job, basically exactly as if you were logging onto Telemetry 3, and you can run programs. And here I run the MPI run hello world. So I was allocated 2 nodes. So it says, well, hello world from this node and from this node. And then when I exit this shell, it says that I have relinquished the allocation and I can keep on working on the front end. So this way of working with salloc is for testing parallel jobs before actually submitting them. But of course, if you do that, it's for submitting maybe multiple times, small jobs, small MPI runs command to see if they complete correctly or to see if there is no error in the logic, just to be able to interact with the job rather than submitting in a computer. Yes.
Okay. So here, for example, we don't specify the time.
Yes.
So is there a time limit or?
Yes. So there is a time limit and there's a default time limit. So there is a time limit for the partition, which is the maximum that you can request for a job, and there's a default time limit for a job when it's not specified inside the job itself. Okay. And that information you can get it from the scontrol show config, if you remember. On the Metro 4, there's a catch. There's a plugin that requires you to set up the time limit by yourself and does not allow the default time limit. Now, if you want to run directly on a compute node, because you've seen here that when I run salloc, I was still on the Metro 3, which is a front end. This is the older version of the Metro 4. If you want to run directly on a compute node, you can use salloc. Salloc will, depending on the configuration, give you a compute node directly. So it's a technical difference which doesn't matter. This is the new way in Slurm of working with salloc. What you've seen with the Metro 3 is the old way, depending on the cluster and how it's configured. And you can have a look at this option to see whether you are in the case of the Metro 3 or in the case of the Metro 4. But now salloc will give you a shell on the compute node, so you can directly here run your program rather than starting them with MPI run if it's not an MPI run command. Not sure it's important, but most of the time, if you just want to have a shell on a compute node, you will run salloc, except if it does not work, then you will run srun like this with --pty--l. It has exactly the same effect if you're on a cluster that is not configured in the modern way. Any question about this? No. So the interest of having an interactive job is either to be able to run small tests and interact with the job, or to run services that cannot start otherwise. Like for instance, if you are using a Jupyter Hub or Jupyter Lab program, you need to interact with it and be able to click to connect to the web page and click on the button. So you need an interactive job. There is no point in having a job start in the middle of the night if you are starting Jupyter Lab in there or RStudio. So you need an interactive job for that. So here are some examples on how you can start a Jupyter notebook on a compute node and connect to it with your laptop with the browser on your laptop. So first, you run here the other version with srun-pty/bash. And then you start your Jupyter notebook. It will tell you some information here, and you need to remember that information because this is what will be needed to connect to the instance running on the compute node. There's a catch that you need to add this option to get information information, to get the entire information that you need. If you start Jupyter Notebook on your laptop, what will happen is that the browser will start and you will be directly shown the notebook. Here, it will complain that there is no browser installed, but it's not an issue. You need to remember this and configure your browser correctly through a proxy tunnel. So basically, you need to open a terminal, run this command, and it creates a tunnel between your laptop and the compute node through the gateway and through the front end. So you need here to choose a number here, which can be between 1,000 and 24,000. Doesn't matter which one, but you need to remember. And then you need to configure your browser in the proxy settings. You need to look, so this is the example for Firefox, but if you are using something else, look for the proxy settings. In the proxy settings, you need to specify that you will be using a SOC5 proxy, which should be localhost. And here, you need to put the number that you chose when you created the tunnel with SSH-D. Well, if you do that, your browser will most probably stop working for other websites. So it's better to create another profile or use another browser for this configuration. But then, if you use the URL that you got from step 2, we can access the Jupyter Lab instance like here. And you see here, this is the internet address of the compute node on which your job is running. So it's not trivial, but it's a 5-step process that allows you to start a web service on a compute node in a Slurm allocation, and then connect to it through the network, through the gateway, through the front end, to have access to the web page. Okay. For those of you who are using RStudio, here is the same process. I will just skip it because it's exactly the same ideas, same configuration of the browser, and then you have access to the RStudio instance running on the computer. And you get this nice interface. If your program is using a graphical user interface and you need absolutely to use it, the same thing here with the VNC, which is a way to have a virtual desktop running on the compute node to which you can have access. Here are the instructions, and the nice thing is that MobileStem, the tool that you are using if you're on Windows to access the command line and the SSH client command line, can be used also to start a VNC session here, and is able to use your cluster configuration to use VNC through SSH, again through the SSH gateway, through the SSH plugin node to get access to a compute node. You need to configure it like this, specify the 2 gateways, and then when you start it, you have here your virtual desktop on the compute node, where you can start programs. So this is a very wide example, but actually if you have a program that has menus and a graphical user interface, it will appear here. Yes. Yes. So you can save the configuration, but you will need each time to submit the job and open the connection in VNC. If you are not using MobileStem, there are VNC clients on Linux and Mac OS, which you can use. The thing is, if you keep always the same port number, you can just restart the commands in sequence, but you need to, when you don't use it, you need to cancel your job and free the resources for it. If you are using VS Code, are there anyone here using VS Code? Okay, you can configure your SSH client in a way that allows you to connect to your VS Code to a running job. So here, what you see is that I'm using this name to describe a host on which I have a job running. So not necessary to understand exactly how it works, but if you copy blindly this to your .ssh config and you submit a job which has the name tunnel, it's important here because it's used here. And it has this command exactly. Here you can put again any port you want. It has to be above 1024 and below 65,000. But you can choose whichever you want, and you can run this. And as soon as this job has started, you can connect to host, and you choose what you have chosen as the name of the connection, and then you have your Visual Studio Code running on the computer. So there you can do whatever you want. You can start even notebooks if you have the notebook extension and so on. But this allows you to use your local configuration, your local development environment on the compute node inside an application. Question about this? Okay, then I'm 5 minutes behind schedule, so we'll stop here. The last exercise was to answer all those questions for your specific case, and actually when you have an answer for every question in there, you are able to write your submission script with this basic structure. And unfortunately, I don't have much time here to let you work on that, but if you have questions afterwards, you can send me emails. The slides are on the Indigo website, so no need to take pictures. It's much better quality if you just download them from the website. Just a few final words. Here are a good practice. I encourage you to read them. Next session about Slurm, I will go through them again. If your job are too long compared to the maximum runtime, there's a checkpointing session this afternoon. If you have multiple jobs and you don't know how to organize dependencies, there's a workflow session this afternoon. If you need help, there's an interactive wizard on the CÉCI website where you can click depending on what type of job you want to do, and you have the job that creates itself automatically on the right part, and you can copy paste it in the submission script on the cursors. And I thank you for your patience and attention. And if you need to keep working on Slurm shell, on the game shell Slurm, you can keep doing so and send me emails if you have questions or if you see bugs, don't hesitate. So good afternoon, everyone. The slides which I'm going to use are on the Indigo website. So feel free to download them if you want. Also, I will assume here that you all know about Slurm, that you want to know my time in the first session, or at least you know the basics. So this session will be about, well, the title I said was Advanced Slurm Submission, but actually it's all the slides which I didn't have time to put in my first presentation. I made a second presentation out of it. So there'll be four parts, and even a fifth one after if we have time. First one will be about workflows with Slurm. So when you have multiple jobs, you want to organize them in a way. The second part would be about the GNU tools and their interaction with Slurm. I don't know if you attended the session where I spoke about xargs, GNU parallel, Make, and all the tools that allow you to work in parallel on the nodes. I will show how we can use them inside of a job or to submit jobs to Slurm. I will also speak about heterogeneous jobs. So jobs where all the processes, all the tasks do not need the same amount of memory or the same amount of CPUs. And then I will talk a bit about process placement in Slurm, because you've seen this morning that Orion mentioned that the new architectures of the compute nodes forces you to think about where the processes are located to make sure that the access to the command memory is optimized. So the first part is about the workflows. This is a slide which I used in the workflow session just to remind you that I distinguish between wide workflows where you have a large number of jobs that basically do the same thing, and deep workflows where you have a lot of dependencies between the jobs. And also there's another category which is called cyclic workflows, where a job needs to requeue itself or to resubmit it itself. So we will see those three categories now. Just a reminder about job arrays. So in Slurm, you have a mechanism for submitting and managing a collection of jobs at once. It's called parameterized jobs as well. The typical use case is when you have a parameter study. So you have the same job to run with multiple values for the same parameter. Or if you have multiple files that you need to process with the same program. Or if you have a large file with some lines in there which each need to be processed by a job. This is the typical use case for job arrays. So the way it works in Slurm, job array, you use the dash array like this, and then you specify a range of indices that the array will take. And you see here 3 examples that you can use. So this specifies a range, this specifies a list, and this is a range with a step. So it's common in many languages to be able to generate sequences. And this is the syntax that is used in Slurm to generate sequences. What happens when you submit a job array? You have multiple jobs which have a distinct Slurm job ID, but they have the same Slurm array job ID. And they have a Slurm array task ID defined as the number of the rank inside the array of the current job. Another thing interesting is that you can use this range notation also to target multiple jobs or same array at once. So if you use scancel, and this is the job ID, and then you put here the sequence of Slurm array task ID, you can cancel a subpart of the array with only one command. When you specify an array, make sure to also mention the array in the name of the output file, because if you just use the -j, or if you're confused, and you can end up in a situation where all the files or the jobs in the array write to the same file, and the last one wins and overwrites everything. So make sure to either use the job ID or the pair, which is often the most useful, job array ID and Slurm array task ID. And so this is a typical usage. In your Slurm submission script, you have -- array equals something, and then you run some program and you give it an argument, for instance, the Slurm array task ID. And this is the part, just like the rank in the MPI or the thread ID in OpenMP, the part that makes sure that all the jobs do not do the same thing, because they all see a different value for this Slurm array task ID. Okay, is that clear for everyone? Okay. So the major caveat is that the parameter array, it must be integer, it cannot be negative, it's only one-dimensional, and it's bounded. Actually, there's a configuration in Slurm which specifies the maximum size for an array. And so this is an upper bound on the range of indices that you can specify in your array definition. Hopefully there's a solution for all these caveats. It's called bash arrays. So basically the idea is in your submission script, you use an intermediate variable bash array in which you put all the values that you want to iterate through, and you use the Slurm array task ID as an index into that array. So here, the params variable, thanks to the parentheses, is created as a bash array. So it's an array in the bash language. And here, this syntax with the brackets here says I want in this array the value whose index is the value of this variable. Okay, so it's an indirection in the bash array. So this is an example. Let's say I have some program and I need to run that program on with 3 different parameters like red, blue, and green. This is all made up for the example, of course. Your submission script could look like this. Dash array equals 0 to 2 because the bash arrays are 0 indexed. So the first item is item 0. Params with the parentheses create an array. So param 0 is red, params 1 is blue, and so on. And so with some program will be run thanks to this syntax in the 3 different jobs with the 3 different values, red, blue, and gray. Okay, is that clear for everyone? Okay, the same idea here. With the parentheses, again, you create a bash array. And if you put here a glob, so a shortcut for list of files, params will contain the whole list of CSV files inside the data directory. Okay, and then same idea here. You will run some program into each of these files in each of the job in the array. And here I assume I have 3 files. So I go from 0 to 2. So the value that is here cannot be dynamic inside the script. So you have to know in advance the number of files in this case that you want to process, because it has to be hard-coded in a sense in that part of the submission script. You can also play with the bash curly braces expansion like this, because remember you can only have integers. So if you want to iterate over a sequence of real values, you can use construction like this. This will expand to 1.0, 1.1, 1.2, and so on. And so you can run some program on 1.0 in one of the job, and then on 1.1 in the second job of the array, and so on. This is another example with curly braces expansion. If you have 2 sets of curly braces, it creates all a pair. So this is 1 red, 1 green, 1 blue, and so on. And so with this, you can use this part of the syntax. If you see, this is different from the other ones. So here, I'm just extracting from the params parameter this element. And here, what I'm doing in addition with simply this is to remove the underscore here. Okay, because with this, if I don't have anything here, it will not do all pairs. So I had to put something here in order to create all pairs. But here I'm assuming that some program needs 2 arguments. And so I need to split this and remove the underscore here. Okay, so because I said that the index is only 1-dimensional. So if you have a 2-dimensional parameter, so here I have 1 dimension going from 1 to 3, another dimension which is categorical with the colors. I can create all pairs with this syntax and use this syntax to split each element of the pair so that my program gets the 2 arguments that it's expecting. Another nice tool is the sec command. If you need to generate sequences of numbers in bash, you can use a sec command, and you can specify with the dash format exactly how it has to look. So if you need, for instance, this notation for the elements, for the arguments, you can use a sec command, put everything in an array, and then use the same array in direction, dereferencement like this to pick the value on which the current job is working. Another nice program, which is available everywhere also, is called map files. the mapfile program reads a file and fills a bash array with the lines in the file. So here, I give it the path to what I suppose to be a parameter file. So with one line corresponding to all the parameters that have to be tested in a way. And I create a params variable using the map file. And so this params variable, again, will become a bash array. And each element in the array will be one line in the file. Okay, you don't need to read a file, parse it yourself, and so on. Just use that. You have a variable in memory, and again, you can use this expression to pick up the line in the file on which you want the element in the array to work. Is that okay for what? Okay. So I said earlier that one of the caveats here again is that you cannot have this kind of syntax inside the submission script. So you have to know in advance how many jobs in the array you want. And if you try to write this in the submission script, you will get this this error explicit. But there are solutions. You have two ways. One way is to specify the dash array on the command line. So you don't specify it in the submission script, but you use whatever bash commands here to look at the number of files, for instance, that you have in your directory, and then you put it in the variable n, or you put it in the params variable, and with this you can extract in n the number of elements in params. And this value can be used here because bash will expand this to the actual value before SBATCH sees it. So actually Slurm will get the value hard-coded as it wants, but you will be able with this to have a value which is dynamic and computed from, for instance, the number of files in the directory. Okay. Another way is to use SBATCH through the standard input. So I'm sure you are familiar with using SBATCH and then giving it the name of a submission script. So SBATCH and then submit.slurm.sh and enter. But actually, SBATCH accepts also the content of the script from standard input. So it could do cat submit.sh pipe SBATCH. So it would be the same. Except that doing so, you can use the envsubst command in bash that is able to replace in a file all occurrences of a bash variable with the actual value. Okay, so if I have in my submission script something like this, and I give it to SBATCH as is, I will have the error that I showed earlier. If I use envsubst and I say, okay, in this file, we place n with its actual value, envsubst will output this where this has been replaced. And then you can feed it to SBATCH, and it will process it. Okay, so it's a way to work. One of the gotchas is that when you do that, in the accounting, you do not have any reference to this script because SBATCH never sees the actual value of the name of the script that you used. It only sees the contents. So envsubst is a nice tool to do very basic level templating. So if you have a parameter file with a value which need to change, you can use envsubst, and actually I will have an examples later on. So this allows having elements in the number of elements in the array to be dynamic in a sense. Here, I'd like to speak about scripted submissions. So again, you're familiar with the workflow where you write a submission script and then you use SBATCH and the name of the submission script. But actually, you're not forced to use a submission script at all. And it's nice when you have job arrays where the jobs are too different and they do not fit in the job array, or if you want to quickly adapt a submission script to Slurm. Quickly adapt a script which has nothing to do with Slurm into a script that you can use on the cluster. So the recipes that you will see here, you should only use them when you have few nodes, few jobs. So too many jobs to do it by hand, but not like 20,000 jobs, because compared to job arrays in the accounting Slurm, in the processing of the jobs, they're all packaged together, and actually they don't use that much memory. Well, here, if you script the submissions and you end up with multiple thousands jobs, when you type squeue, you see all the jobs, and it imposes a large burden on the scheduling. So what I'm talking about is this. Assume you have a submission script like this. You can replace it with simply those two lines. So here, what I need to do is create or specify the environment. So typically, the first step in the job submission script is to specify the environment, so the modules that you want to load. Here, I need to load the module right away on the command line. Then all the parameters, I need to put them on the command line, and the part which is the actual step or job step that the job must run, you can put them in a parameter called wrap. So if you run this, it's mostly equivalent to submitting this job. But the nice thing here is that you can play with that. And so you can have for loop, for instance, here. I use SBATCH, wrap, and then MPI runs some program. And you see that here, the variable goes from 4 to 32. So if you need to submit multiple jobs, each with a number of tasks which increases, just to see how your job scales, you can do that in one line with this, simply with a for loop. And the -wrap options, which does not make the step of writing a submission script necessary. So this is a second example. If you have a script like this that works on your laptop, you can put it on a cluster and replace the line here with SBATCH and then wrap, -wrap, and the line here. And so this will submit one job to the cluster for each of the iteration. So for each of the 5 in the example here. Okay, so -wrap is a way to not have to write a submission script. Any question about this part? So set of little tricks to play with Slurm, mainly with arrays. And now we'll move on to the second type, which is where you use the -- dependency. So in Slurm, you can submit jobs all at once and request Slurm that the order in which the jobs are scheduled is based on the constraints that you imposed. A typical use case is like this. You have a pre-processing job that prepares the jobs. Most of the time, it does a lot of I/O, copying files here and there, I don't know. And then you have the actual processing job, which often is larger, uses a large number of nodes, and then a post-processing job, which collects all the results and packs them to something. They are distinct jobs, but you don't want the post-processing job to start before this one has ended. And at the same time, you don't want to wait until this one has finished to submit the other job. You just want to submit all of them and just wait. So you do that with the -- dependency. And -- dependency accepts a parameter list, which looks like this. So you can specify after bus buffer, but we don't have any here. This is for job arrays or after not okay. So you can specify, I want this job to start only if this other job has completed correctly, or only if this other job has started correctly, or only if this other job has failed. And you specify a list of job IDs here. So you can say after this job ID, or this job ID, or this job ID. So if you specify a list with comma, it's a logical end. If you specify a list with a question mark, it's a logical OR. I will show examples right away. So here I have one submission script called preprocess.sh, one called process1, process2, and then I have post-process, I have cleanup, and I have cancel. Okay, and what I need is that pre-process is started first, that process1 and process2 are only started after pre-process is completed, that post-process only start after process1 and process2 have completed, that cleanup is started when they are all finished, and that cancel is started if either pre-process or process 1 or 2 has failed. Okay, you see what the requirements are. So what I say is that process 1 must start after OK of job ID 1. Process 2 also must start after OK process job ID 1. Pre-process must start after OK job ID 2 and 3, so those two. Cleanup must start after jobs 1 to 3, whatever. So after any means whatever completion status they are in. So either completed or failed. And then with this, I specify that cancel must run if any of job 3, 2, and 1 have failed. Okay, with this you can organize your workflow and already submit all the jobs at the same time, and you don't have to worry about it. Just let Slurm do the job. Depending on the configuration of Slurm, jobs whose dependencies would never be satisfied must be dealt with. This is why I have a cancel.sh here. So if a job depends on after OK of some other job and that other job fails, the dependent job will stay in the queue unless the Slurm is not prepared to kill them. But it's not necessarily the case of the whole cluster. So it's always a good idea to have some kind of cancel script at the end where you can clean up everything if there was an issue. One of the caveats is that here you have to specify a job ID. So you must first submit this to get the job ID, and then you can use the job ID in the command here. There's a little option to help with that. It's called the -- parsable option in SBATCH, because by default, if you submit a job, it will tell you that job number has been submitted. But what you need is only the number, the job number, not the whole sequence or the whole sentence. So you can use -- parsable. And this is a little trick also. The after OK here is only active if the job ID exists, but it will not fail if the job ID does not exist. So if I specify -- dependency after OK and then a job ID that does not exist, like this, for instance, if it's a very large number, it will just submit the job as is and it will work. So you can do something like this, assuming I have 4 scripts in my directory: submit script 1, submit script 2, and so on to 4. If I do this, you will see that it will SBATCH the first one, $R is 1. This will just be ignored because GID is initialized with a very, very large number. I use -- parsable, so the output of this is only the job ID, and I put the job ID in this variable. And then the next iteration, I submit script 2 with a dependency on job ID of the script just before. So if I run this, I will just submit the 4 scripts with a dependency of script n on script n minus 1. Okay, and sometimes you have a sequence of jobs which you need to submit. With this little recipe, it just does the whole one. Another thing you can do, if each of the steps in the sequence is short enough to hold into a single job, you can do something like this. So rather than submitting 4 jobs for the 4 steps or the 4 elements in the sequence, you can submit 1 job and use srun in the for loop exactly as before. Rather than submitting 4 jobs, you pack them, as you say, in a single job script with a for loop to just iterate. And here, because it's in the same job and you have srun inside the loop and nothing else, the elements here will run in sequence. So you can have, you're sure here, just like before, that the some program 1, 2, 3, 4 will run in sequence, which is not the case if you just submit 4 jobs and you do not organize the dependencies. Okay, so when you have multiple stages, you can either create multiple jobs and chain them with the dash dependency, or pack them in a single submission script with srun like this. So here, I just mentioned that these programs will run sequentially because srun, without further instructions, will use the entire job allocation. But you can also do something like this, where you give to each instance of srun a sub-allocation, so a smaller part of the allocation. So here I'm requesting 4 tasks, and I have a for loop that goes to 4, and I say srun use only 1 task. And if I do that with the --exact option, this program will only have access to 1 task, so 1 CPU also. Which means that if you put an ampersand here, and the jobs, the srun commands go into the background, they can all run in parallel using each 1 task of the 4 task job. So if here you go above 4, what will happen is that all the srun commands will be instantiated at once, but the one which do not have access to the allocation, so the first one will get 1 task, the second one, the second task, and so on. And then the 5th one will be blocked by Slurm until the first one is finished. Okay, so here, if I have 1 to 8, they will go here 4 by 4. And you will see explicit messages saying that there are no resources in the allocation anymore, and that the sruns which do not have access to resources are put on hold, are sleeping until they get free access. So if you don't put the exact here, srun will inherit the whole allocation. So it's the keyword here. If you want, you can also use --overlap to ask all srun instances to start at the same time, and so to fight for the CPUs. If you know that your program is meant to be run like this, you can force them to say, okay, I know that I have more processes than I have CPUs, but I know that the processes are not CPU bound, so you can pack them 2 by 2, for instance. But by default, Slurm does not like this situation, so you need to use --overlap. The --exact command is the --exact parameter is pretty recent, and it has a long history. I'm not going to go into details. Just the information is that if you have access to a cluster where the version of Slurm is a bit older and the --exact command is not recognized, just replace it with --exclusive. It's not the same --exclusive as you use in SBATCH when you request a full load. In this context, on the older versions, it has a specific meaning of the --exact command parameter that was introduced later on. Okay, so use --exact, except if it's not recognized, it's safe to use --exclusive. Questions about this? No? So now I'm talking about jobs which need to be requeued. So if you remember the session about checkpointing, it can happen that a job needs more time than you actually are allowed on the cluster. So you need to stop it, save everything on disk, and then resubmit the job to pick up from where you left and keep on the recount. So it's something you can insert into your job submission script. You see, if some condition is met, which depends on what your program does, you can use scontrol requeue and your Slurm job ID, and this will just requeue the job. I don't have any other explanation. So it will keep the same job ID. It will start again in the queue in the pending state, and then Slurm will allocate resources. Slurm will tell you how many times it has already restarted by setting this variable. So from within the script, you know if and how many times your job already has been requeued. When you do that, it's also useful to use --append, and this makes sure that when the job starts, it does not overwrite the output and error file if they are already existing, because you want the history of the job. And if you don't put that, you get only the output of the last job. You can also use a feature which is configured on most CÉCI clusters, I believe, which you can check with this. So this requeue exit is a number, and this is the number that you can use when you exit to tell to Slurm that you want your job to be requeued. So for instance, the same this scontrol requeue can be replaced with this exit 99, and this will make the submission script exit with the return code 99, and in the configuration it's configured to be linked to requeue exit. So if Slurm sees that the job exits with 99, it will requeue the job automatically. So there's not much difference here with what you've seen before in terms of functionality, but here what's important is that the number here can be exited by this program, so you can put it in your program. If your program exits with code 99 and it's the last one in the job, then Slurm knows that it has to requeue the job, and it can do that for you automatically. Another way to work is use SBATCH inside the submission script. So inside the submission script, when the job is running, you are able to submit another job or submit the same job. So here, if you write this, SBATCH $0 will submit a new job, so it will be a new job ID, but the job submission script will be kept. So $0 inside the bash script refers to the path of the script itself. So of course you need to put some condition here, otherwise you would just resubmit and resubmit until we quit, basically. So there are multiple ways to resubmit the job with two different paths. Either you can requeue or resubmit. If you requeue, it's the same job ID, so the same output files. If you resubmit, it's a new job ID, so new output files. Depending on your workflow, you might want to you might find one more interesting than the other. Any questions about all of this? So it's other ways to use Slurm to submit jobs than what I have explained in the first session, which was more basic level. No questions? Okay, I will move on to the second part then, and see how we can use the tools that we've been talking about in the parallel computing session in the context of Slurm. So a quick reminder, who is familiar with the xargs command? Not everyone. So a reminder, xargs is a command, bash command, which reads a list typically from standard input and a program on its command line. And what it will do is run the program on each of the items of the input, standard inputs. So for instance, here what you see, the find command is looking for files in the directory. The dot here means the current directory, and I'm looking for files whose name ends with .csv. Okay, and the find will list all the files in all the directories that end with .csv. I feed that with a pipe here to the standard input of xargs, and xargs will run SBATCH, and because I put here this element, it will replace this part here with what it has found in its standard input. Okay, does that make sense? So I have a first find command. It will give a list of files, basically, and xargs will take each element in the list, each file, and feed it to SBATCH at the place where I put this placeholder, which is referred, which is the same as here. So I tell SBATCH, I tell xargs that I'm going to use a placeholder written like this. I can use anything else, but this is a standard way of working. And then I put it here, and so it will run SBATCH. So if you have a directory with a large number of files, and you need to submit one file, one job for every file, you can do that in one command with this. If your program here is too short to justify the fact that you want one job per instance of the program, you can do it like this. The difference is I'm inside the submission script here, and I'm using the xargs with -P, where I limit xargs to the number of tasks that I've requested in my submission script. So I'm telling xargs, work in parallel, but no more tasks than this number, which is defined by what I have put here in the arguments. And then I use srun and --exact with some program, and again, this placeholder. And so this will do exactly the same thing. Look for a list of files in the current directory with file termination in CSV, and pass them through xargs to srun, so that srun instantiates this program for every file, and the parallelism is managed by xargs and Slurm together. Okay, does this make sense? So either your program is very heavy and you need to have one job per instance, or it just does some conversion which is very fast, then you pack everything in the same submission script. You can use also elements in a file. So just before I used xargs with find, and find generated a list of files, but it does not need to be a list of files. If you have a file called parameter.csv, you can use xargs the same way as before. It would split each line, and each line will be introduced here as parameter of the some program. So here I wrote CSV, but it can be any line basically that you want to appear here. So it could be some parameter, some options or command. They will be interpreted by bash just as if they were written on the command exactly. Again, two different way of working. xargs running SBATCH to submit one job per instance of the program, or xargs using a starting srun inside the submission script, so that you pack all the instances in the side of the submission script. Okay. I talked about envsubst just before, but here I will show you an example a bit more convoluted. So envsubst takes the text in standard input and pass it to standard output, and in the process it removes all the instances of the variable and replaces with the actual value of the variable. And this is very useful when you are using a program that does not read parameters from the command line, but where you are supposed to put every parameters in the file and read the program when it starts reads the file. There are some scientific software that work like this. And in that case, envsubst is pretty useful. So assume here that I need a file called input.txt, and in the file I have 3 variables defined: nprox, toll, and max iter, just made up for the example. And I need to submit multiple jobs that all have different values for these 3 variables. So I can write the input.txt like this. I can set up variables in the environment that have actual values that I want. And with envsubst, I can insert all the values where the corresponding variable is written. Okay. So you can do something like this. With the same example as before, I have, rather than having a single value here for each of the variables, I now have for each of the variable an array, a bash array with the 3 values that I want to use. And so I can use a for loop where first I pick up from all 3 arrays the ith element and put it in the variable, the same variables that are defined in this file. I use envsubst with the template and the variables defined to generate a specific file where the variables have been replaced by their values. And then I use SBATCH --wrap and the name here that was generated here. Okay, so this is a way to have a template for a parameter file for a job for a program, and use envsubst to replace the variables names in the template with the actual values. All good? Continue. Okay. So now I'm talking a bit about GNU Parallel. So GNU Parallel is a tool which is installed on most of the clusters. You can have a look. Who is familiar with GNU Parallel? A bit. So, but not everyone. So a quick recap on how it works. When you start a command like echo with parallel, and you use the triple colon and the list here, what parallel does is run the command here on each of the elements of the list. Okay, and it does that in parallel. So this would be equivalent to running these with the ampersand at the end and have those run in parallel. The nice thing is that you can use anything you want to generate the sequence. So here I'm using a bash extension, but it could be using the sec command. I can use globin. So if I have 3 files in my directory and I run something like this, it would just echo all the 3 files. So you see already that it's a nice tool to start processes in parallel. Just like with xargs, you have placeholders here, which are replaced with the elements of the list. So if you do something like this, you end up with the list here, where the curly braces have been replaced with the elements of the list. And there are specific syntaxes which you can use inside the curly braces. For instance, here to strip the last part of the job name or the file name, or with a slash to strip the directory part of the path. You can also use multiple sets. So if you have multiple times 3 columns, Parallel will compute all pairwise combinations. So if I use echo and you see the placeholder here, 1 refers to the list here and 2 refers to the list here. So I have 1A, 1B, 1C, and so on. And Parallel does all the computation. You can have multiple sequences there. If you put a plus there, it will only use the corresponding indices. So 1A, 2B, 3C, depends on what you need. Sometimes you will need all pairwise combinations. Sometimes you will just need the list of with one element of each of the lists. And you can use this syntax also with 4 columns here, a file here, which can be, for instance, a file like that, comma separated values with a header and column names. And in the end, GNU Parallel will read the file, recognize that these and these are the column names, and use the contents of the file to do whatever you want, basically. So here I'm just using echo, but basically this is a way to just run one program on each of the elements of a line of a CSV file, for instance. There are many options. I will not go further here. But the main point is that what I showed with xargs and Slurm, so xargs to run SBATCH or xargs to run srun inside the submission script, you can do this exactly with the same with Parallel. So you can run Parallel SBATCH -- wrap and then some program and here the element that you want, or do the same thing inside the submission script. And you see that it's an old version of the slide, because here I should have exact currently, not exclusive. It is the old way in Slurm to do the same thing. So basically everything that we did with GNU Parallel in the parallel computing session, we can do it either to submit multiple jobs or to run multiple steps inside a single job. Okay, the same will actually be true with GNU Make. So if you attended the Make session or the workflow session, you know about Make, but I can quickly recap. So GNU Make is a tool which was designed initially to build software, so go from the sources to the compiled version, making sure that the dependencies between the files is respected, but it's not limited to that. Basically, it takes a file which looks like this to specify a target, which most of the time is a file, a set of dependencies, which also can be files, most of the time are, and then commands that go from the dependencies to the target. And the nice thing is that if in the dependencies here, here's the name of a target, GNU Make knows that in order to build this, it first needs to build this. So this is an example where I have a make file that first creates a file in a directory, and then from that file creates an archive with a tar command, and from that archive create a compressed archive with the gzip command. Okay, so just an example to show you a real example. And so if you run make, it will look for the make file in the directory and will do everything. And if you run it again, it will just notice that the timestamps of all the files are in the correct order, basically, and it will do nothing. So if you remove one of the names of the files and you run the make, and this is the last file that was generated, you just rebuild it based on what still is in the directory. Any question about make? Okay, this was just a quick recap. The nice thing is that in make, you can specify the shell. So by default, the shell is bash, but it does not prevent you from, sorry. So before I say that, just like xargs, so GNU Parallel, you have a -- jobs option here, which specifies the maximum number of recipes or rules that make will run in parallel. So if you compile a program and you run make -- jobs 12, for instance, it will use at most 12 CPU to build all the programs or the libraries that are used in the program. So if you have a program that uses 10 independent libraries, it can build all 10 libraries and pack everything at the end. And it can give it a maximum number here. But what I wanted to say earlier is that you can replace the shell with srun and specify arguments here to be n1, c1 exact, for instance, and then bash-c. And what this will do inside of a submission script will run every item in the make file as a step in the job Slurm. Okay, so just like we've seen before with a -- exact, here you can take a make file which was designed outside of Slurm and put a small header like this, and all the sudden it becomes Slurm compatible, and it will do everything inside of a Slurm allocation and distribute the work to the processes, to the CPUs that were allocated to the job, honoring the dependencies between the recipes. Any question about that? Then we'll move to the next part. And the next part is about these type of jobs. So there are typically two main situations where you might want that not all the tasks in the job have the same access to the same resources. If you have a master worker setup, or if you have a coupled simulation model. For instance, Orion mentioned earlier in the API session that there's a oceanographic model called NEMO that works in parallel with xargs, which is another tool to handle IO, basically. And NEMO can also be coupled with other models, ice models or atmospheric models. But the requirements for xargs and NEMO are not the same. With this, you can specify in your job submission script some parameters for one of the pack jobs. So Slurm calls them the pack inside the job. And if you use a SBATCH pack job option here, Slurm will understand that this set of options is for the first part of the job, and these options are for the second part of the job. And you can use it like this. Then inside of your submission script, you can use srun and then say, okay, I want to start this process on this group. So this group has been allocated. Sorry. The resources that are described here. And the second group, so worker group called 1, have been allocated the resources which are described here, all inside of the same submission script. Note that if you do this, worker and coordinator, which can be MPI programs if you want, will not be part of the same communicator because they are started with two distinct instances of srun. So they will be working in a distinct communicator. So you can use MPI in this setup to communicate between these two. But there are other ways to communicate between the markers. So if you need every instance to be part of the same MPI work, you need to run them like this. So srun, and then the first one, colon, and the second one. If you write it like this, Slurm will run this program on the set of resources that are allocated corresponding to the first part of the job, and this on the set of resources allocated to the second part of the job. If you prefer to run MPI run rather than srun, you can do exactly the same with a colon here. Okay, it was quick because nothing much more to say about heterogeneous jobs. Any question about that? No, this is a syntax which is not often used, but if you see it now, you remember what it's about. It's a heterogeneous job where you can have one part that has, for instance, like here, 2 CPUs, 1 GB of memory running on the main partition, and here only 1 CPU but 4 GB of memory running on another partition. This is something important to note. Normally, you cannot have a job that spans multiple partitions. So when you submit a job, it needs to find all the resources into a single partition. If you specify multiple partitions on the -- partition option, it will try every partition in the list, but it will never split the job across a partition. Except if you are using this kind of job when you can say that, okay, I want this part to be in one partition and this part to be another partition. So typically, you can have here, for instance, a partition with the GPUs for computing and a partition here with fast disks for storing data, and it will organize the job on those two partitions based on the resources that you have requested and on the programs that you started with either this option or this syntax. Okay. So now I'd like to speak about process placement, but here I know much less than Orion does. So if I say something wrong, Orion will tell me, and he will correct me. So if you remember the first session, I explained about n tasks per node, and nodes, and then and I said that there were multiple options to request a number of nodes or a number of tasks. And the thing is, sometimes in some applications, it's important to decide, or at least to know, how the tasks are distributed over the resources that are requested. Why is that? Because here I show you two different, let's say, communication patterns in two different jobs. What I have here is description of a job where process 1 and 3 exchange a lot of data. Process 2 and 4 exchange also a lot of data, but 1 and 4 do not. 1 and 3 do not either. Okay, so this is what those arrows represent. And here, it's another job, another situation where 1 and 3, 2 and 4 do not communicate a lot, but there are a lot of information passed from 1 to 2 and from 3 to 4. Okay, so two different hypothetical jobs. In both cases, you would want the process IDs to be distributed differently. So here, because those two processes talk a lot, you want them on the same node so that they don't need to use the network. They can use the memory, which is much faster to communicate. And here, between these, because you don't have much to communicate, it's okay to go through the network. Okay, here it's the opposite situation, where you want actually 3 and 4 to be on the same node, again for the same reasons, and 1 and 2 to be on the same node for the same reasons. And actually, this you can organize within Slurm with the -- distribution option. The short version is -m. It's a complicated option, so I will go step by step. Here, two examples with two different values for distribution. Here block, here cyclic. What I'm doing is requesting 4 tasks on 2 nodes. The L here is an option to srun to say, okay, I want you to prefix every line in the output with the task ID. So this is why I have 0, 1, 2, 3 here, because I put here the -l option. For the example, I use -- exclusive, because actually you cannot use options to precisely place the processes on a node if you don't request the whole node. Because Slurm can only activate those options if you request a full node. So I have here -- exclusive. I'm requesting srun to run hostname, and in block parameter, distribution option, what it does, it puts 0 and it fills the nodes with the instances. So with 2 nodes and 4 tasks, with block, it will have 0 and 1 on the first node of the allocation, 2 and 3 on the second node of the allocation. Okay, so this would correspond to the first example I showed. If you want the opposite, you can use cyclic. And here, what Slurm will do is put the first task on the first node of the allocation, the second task on the second node of the allocation, and then the third task, because there are 2 nodes, back on the first node. So it's cycling through all the nodes. And you end up with ranks, MPR ranks, which are distributed completely differently. Okay, is that clear? So now that you know how to distribute tasks among nodes, you need to realize that inside a node, as Orion explained earlier, there are sub-nodes in a way. There are NUMA nodes, which make it important to know which CPU has access to which memory. So in the past, the computers were more like this. So it did not matter if process on this CPU needed memory from this part of the server or this one. The path was all the same. On a modern computer, if a process running on this CPU needs access to memory residing in this part, it first has to communicate here to get access here. And so this is slower than accessing the memory which is here. So it has an impact on the overall speed of the job. And you need to be aware of it and organize distribution of the processes in a way that you make sure you're at least doing the least amount of cross-CPU access to memory as possible. And this is something you can have a grasp on using the second part of the option here. So you see again the -m option block, as I just said, refers to how the processes are organized, or the tasks are organized among the nodes of the allocation. And cyclic is about how the tasks are organized on the sockets on the node, so on the physical CPUs. And here again, you see there's a difference, block and cyclic you can use. So here I am requesting 4 tasks with 4 CPUs for each task. And I use exclusive. And so I did not explicitly say that I only want 1 node, but I will get 1 node because with the exclusive, I request a full node. And on a full node, I can place all the 4 tasks with their each 4 CPUs. And what you can look up with a task set option with -cp and then the process ID is the numbers of the CPUs which are allocated to the instance, to the srun instance. We call that the affinity list. And so if you use block, the second parameter, you will see that task 0 will get the 4 first CPUs. So each task needs 4 CPUs. And then the second one gets the next 40 sequence. And the second one gets the next 40 sequence. So that means that Slurm fills a full socket or a full chip before going to the other one. By contrast, if you use cyclic, you see here that the task 0 has access to CPU 0 and 3, which are on socket 1. But task 1 has access to CPUs 32 to 35, which on the examples here is on the second CPU. And then back to the first CPUs for task 3, number 2, and the 4th task, so number 3, is back on the second socket. Okay, so with this, you can organize how the processes are organized inside the node. There's also fcyclic, which you can use rather than cyclic. And what it does is iterate in a cyclic fashion over the CPUs here. So with cyclic, you see that all CPUs from one task are still on the same chipset, while here you see that they are split across 2 CPU sockets, so 2 chipsets. So the first task has 2 CPUs on the first socket and 2 CPUs on the second socket. Okay, does that make sense? And the third option to distribution, which is about the CPU threads, the core threads. So if you remember the first CPU session, the first Slurm session that talked about the threads and hardware threads. So basically each CPU on the cluster can run 2 programs at the same time. Let's make it like this. And sometimes it can be beneficial for your program, sometimes it can be harmful. You need to test, if you are not the writer of the program, you need to test which situation is best for you. And you do that in Slurm with the third option of distribution, but most of the time it will be easier to use the --int option with multi-thread or no multi-thread. So the third option, you can drop it completely and use --int. If you know that your option, your program can benefit from using hardware threads, you use --int equals multi-thread. If you know for a fact that your program is purely CPU bound and it cannot go faster if you add hardware threads, you can use no multi-thread. So you've seen in Slurm you can specify how you want processes to be spread across nodes, how to be organized inside the node across the sockets, and how on a core they can be organized either 2 by 2 or just 1 by 1. But there are intermediate levels that Slurm does not necessarily take into account. So this is an example of one CPU with 4 NUMA nodes. So even though you have only one chip inside, the structure makes it non-symmetrical. And you see here, this is a core with 2 threads and access to some registers which are specific to the core, some which are common to all the CPUs on the same NUMA node, and you have multiple NUMA nodes on the same core. So this is just to illustrate the fact that it's not completely homogeneous. And sometimes it can be beneficial to have your processes either completely spread or completely packed on the same node. So the differences are if you are in this situation, basically what you can see is that this process has access to this whole memory at once. So the local memory that it can use is larger than when it has to share it with other processes. So these 4 processes have these levels of cache which are specific to them, but they need to share the register here, so the memory, the cache here, which is common to all of them. And the cache is important to fasten, to make access to memory quicker. I think I already explained that. But the drawback is that when this one has to communicate with this one, they need to go through the memory and back here. While here, when this one and this one want to communicate, they can read and write to the same portion here. So they don't need to go to the main memory to communicate. So either you have a situation where each process has access to a large local memory, where it has to go further away to speak to others, or you reduce the amount of memory that you can have per process, but then the inter-process communication is faster. So here again, there's no magic recipe to know in which situation you need to be in order for your program to go the fastest possible. But once you have identified which situation you would rather be in, there are tools in Slurm to decide to force that. And this can be done with the --CPU bind option, where with the sub-option map CPU, you can give it explicitly the numbers, a sequence of the number of CPUs that you want to use inside the node. And Slurm will start the processes on the CPUs or the set of CPUs that you have decided by yourself. So for instance, here I use map CPU, and then I give it a completely random list in order of CPU numbers. And if I use, again, a task set as before, I find back the numbers which I requested Slurm to use. Okay, so this is an example which by itself is not interesting. But the nice thing is that the OpenMPI project has a tool called HWLock distrib, which is able to look at the configuration, the hardware configuration of the node, and come up with the best situation to spread the CPUs, the processes at best. So if you are If you want this, it's easy because you just specify from 0 to the number of tasks you want. You don't need to compute anything. But if you want this, you need to compute the process IDs here, 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 and here to be able to give it to Slurm in the correct order. And to do that, you can use hardware lock strip. You give it 16, which is the number of CPUs that you want to use. And then this part here is to write the information there in a way that Slurm can use. And I put everything in a variable called D. And then if I run srun with CPU bind, map CPU, and then this here, I have here each process set up by Slurm on the CPUs exactly that I have chosen. Does that make sense? Yes. So sometimes it's not enough to decide where the processes must run. You also need to decide which process you need to run. So if you have a heterogeneous job, like I mentioned earlier, here assume that I have two executables, model 1 and model 2. Maybe this is an ice model, this is an ocean model, and they need to be spread in a certain way. You can write a multi-prog configuration like this. I explained this in the first session. So with srun -- multiprog, you can ask srun to run a different program based on the task number. And you can use a CPU bind again like this. So with this setup, you can decide exactly how the two models are distributed on the CPUs of the machine. So most of the time, it's important to have heterogeneity in homogeneity in the distribution, depending on the resources that are requested by all of the processes. And you can organize it all like this, or you can organize it all like this. Here again, I have two programs, and the pattern here is different. I want all the first tasks to be running this, and all the next one to be running this. And so with something like this, you can here again put exactly the list of CPUs that you want, and you start this program, which I didn't show. Okay, yeah, it's this program. So this is not part of this program. This program is this, and you run srun with the program, and it will execute the program here or here based on this pattern and the Slurm proc ID. Okay, so if you request 16 tasks, it will first start 4 times this one, then 4 times this one, then 4 times this one, and 4 times this one, and this is computed by this single line impact. Any question about that? I'm not sure that you will need that in all your program, but if you are running on larger machines, it could be important for the performances of the job. Anything else to add? No.
Well, if you are in public MPI plus LP, then it's not map CPU, it's mask CPU that you need to use with mask.
Yeah, so if your each task has multiple CPUs, here you cannot specify a list of CPU, but you need to specify a list of masks, and a mask is a set of CPU in a way. But then it's not map CPU, but map mask. Any question? No more questions or comments? Anyway, so I talked about workflows with slurms and job arrays and how you can change jobs. I talked about how to use the GNU tools that we've seen in the paracomputing session inside a job slurm or to submit multiple job slurms. I've been talking about heterogeneous jobs, and I've been talking about process placements. And if you have still a bit of attention, I can move on to a second part about debugging, submission script, and also best practice. So here, just to learn some more tips, sorry. And the first one's about debugging SBATCH options. When you have a job which does not look like what you initially wanted, this is the things that you need to have in mind. First, there's no variable expansions in SBATCH directives. So if you have a $, something in the directives, it can make Slurm behave weirdly. Slurm stops reading directives after the first command. So I mentioned that also, but it's a very, very common mistake that you have in your submission script, SBATCH something, and then date, and then SBATCH something. And the last SBATCH something is not interpreted by Slurm. So maybe you requested 10 gigabytes of memory per CPU, and your job is killed because it used more memory than 1 gigabyte, and you don't know where this gigabyte comes from. It's from the fact that the 10 gigabyte request was hidden in Slurm, so you end up with the default value, which is often very low on the cluster. So important to keep in mind, and also to keep in mind that the parameters can be set in the script directives, directly in the script, but also on the command line and in the environment variables. So it can happen that you have environment variables defined and you're not aware of it, and it contains some information that influences the way Slurm creates or organizes the job. So it's important to know that your environment is clean before you submit the job. Just to have a safeguard, you can ask Slurm with the -- verbose and with -- test only to first have a look at the script before you actually submit it. So the part -- test only is a part where you ask Slurm to only look at the job and do everything as if it were to submit it, but not submit it itself. So sometimes it's called a dry run in many other environments. And verbose is to give you more information. So it looks like this. It tells you, okay, this is a set of options that I have found. And so make sure that you review this information. And there you should see everything that you asked explicitly and also everything that was implicit. So if you see something here, for instance, 1 task, and you know that you requested 10 tasks, you know that there's an issue in the submission script. And you need to look in the submission script before you actually submit the same job without the -- test. So -- verbose is very interesting to know what Slurm has understood from your submission script. The second thing that is very useful, and you can ask your sysadmin to install it on the cluster if it's not the case. Yesterday it was not installed on NIC5, and then this morning it was installed. I don't know what happened. But basically, it will use the syntax highlighting of Vim to highlight the parts which are probably in error. So here you see an example with -- error with only 1 R. So there's a typo here, and it's written in it's highlighted actually. Here the time format is not consistent with what Slurm expects, and this part is highlighted. And you see, actually I don't know if you see, but the color of this and this is different because this is a correct SBATCH directive, and here there's an H missing. So this is interpreted by Bash and by Slurm as just a comment, and the difference here should be visible in the terms of colors and boldness. And so it's a very easy way to spot mistakes very early on when you are writing the submission script. Can prevent you a lot of mistakes just by using the highlighting in the Vim. And of course, Vim is a software that you should be using to modify files on the clusters. And if you don't know how to use Vim, there are videos of previous sessions on how to use Vim. Any questions about this? No? So now I move on to debugging script logic. So we've seen how we can ask Slurm to help us and Vim to help us with script parameters. And here is about the script logic. Something that should be at the beginning of every submission script is this set of 2 lines. And what they do is asks bash to change the behavior to be safer. For instance, the -e asks bash to stop immediately if at some point it has a command that fails. So by default, if you create a script in bash that says mkdir something and then cd this something, if the mkdir fails, it doesn't matter, and bash goes to the next session. So if you create some file, then after the cd it has failed, and you end up creating files in a directory which is not the one that you intended. And most of the time you will want the bash script to fail as soon as there's an issue in the code. One of the options also, this one will fail is a variable is not defined. Otherwise, bash will just happily run the script with variables which are not defined, just replacing with blank. And so this is important in situations like this. Yeah, you spot the mistake here. Okay, so because there's no L here, local scratch, this variable does not exist, so it's purely empty. So cd brings you to your home directory, and this just erases everything. Okay, if you have the same script but you have this here, it will fail here, which is what you want, I'm sure. Another good practice is to try to trap errors. So the second set of lines should be something like this. You just copy paste this line as is at the beginning of your script. And when it fails, if it fails at some point, rather than saying that it fails, you will have a nice command line, a nice output telling you on which line it failed, with which command failed, and it will write this just below the error. So rather than having just the error message, you have the line in the bash script and the name of the line, and sorry, the content of the line. And that's super interesting when you have multiple scripts which call each other, because at some point you can have an error in a script called by a submission script and called by another script, and you end up not knowing where you are. With this simple line, you know the file, the line, and the content of the line, and the error message. And it's very easy. You just copy paste this line as is at the top of your submission scripts. Also interesting to do is segregate the errors and the comments using standard output and standard error. So if you write echo some comment, this will the string there, some comment will be returned to the standard output. But if you write the redirection like this with larger than ampersand and 2, it will write this to standard error. And so if you write in your submission script a different name for the errors and the output like this first command will be written in out.txt, and this second one will be written in r.txt. Okay, so Slurm has the feature to split standard error and standard output into two different files. So you can write to either files depending on the stream you are writing to. And if you want to write to the error, you just use these redirections in your echo command or in any other command that you write there. If you have a program and you know that, well, basically, if the program does it by itself, it will be split by itself. But if you want to write in the different files, different information, you can use this. That clear? Yes. Another thing that is interesting is that you can increase the verbosity of bash. So if your submission script starts with a shebang like this, so bin bash or user bin and bash, if you add this, what bash will do is write the line before executing it. So if you look at the example here, this is what you actually get as output. So this is the actual result of your program. and this is what bash has been doing behind the scenes. So you see here the content of the variable, the content of this variable. So this line has been executed like this, and you get the actual information because you asked bash to be verbose about it. Sometimes it can be very verbose, but you can filter on the plus signs if you want to remove a bit of the information there. Bash also has a dry check, dry run mode. If you run -vn, bash will just make sure that the syntax is there, is correct. Okay, so the thing is that bash executes line by line. So if you have a submission script with 100 lines and the first 99 lines are correct, but the last one has a problem, just a bit simple syntax error, your script will start, your job will start, will do the 99 lines, and then will fail at the very last line. And you can spot that directly with this. Just ask bash beforehand, okay, are there no obvious syntax errors in my script before you actually submit it to the cluster. You can also use shell check. It's both an online tool and a command line tool that you can use. And here I show you the online version on the web at this address. You can put here your submission script, and shell check will tell you every problem that could happen in the submissions in the bash script. So basically here it complains that when you do something like this, you should put quotes here and here because the way bash interprets spaces in file names, basically. So it's always a good idea if you have a submission script before you submit it to run it through shell check and implement everything that shell check tells you. There are also ways to tell shell check that you know it's not a good practice, but you want it to be so, so that shell check does not warn you about it. But basically, you can trust it. Another nice little feature of bash to debug is with the trap. You just put this at the beginning, so trap read debug. What it will do, it will run the read command because of the debug here at every step. And the read command will actually wait for you to type something or just push enter. And this is a way to just have bash ask you a confirmation for every line. So when you have written a file, a script, and you want to go through every line, line by line, and make sure that everything is okay, you use it with the -v option. And so what will happen is that you will see the line, and then it will say read, and you can put enter, and you see the next line. If you realize here that this line is a mistake, you type Ctrl+C. So it's not a full debugger, but it's a nice way in 3 words to have a confirmation before every line is run. Okay, is that clear? So just small tips to instrument your submission scripts. Because that's always nice to have access to the errors and to tracing and know where the problem is rather than having to look for it. Something important, if you have a large job array, first submit a 2 jobs array just to make sure that everything works. There's no point in creating a very large array if it fails after 1 job. It will just fail all the other jobs in sequence. If there are debugging partition, don't hesitate to submit jobs there to make sure that the overall logic of the script is correct before you actually start a very large and long job. Also, you can use salloc to just test each of the parameters in your submission script. So every parameter in submission script is given to SBATCH, but you can give the same parameters to salloc, and salloc will just create an allocation and give you a shell on the node, and it allows you to make sure that the environment that is created is exactly what you what you need and what you want. Any question about everything that I said here? So just put the trap, the EUO pipe fail, and also the read, trap read debug at the beginning of a script, and it should be safer for you to submit scripts on the cluster. Any question about everything I said? No?